All right. So what topic did we cover? So we looked at Kennedy's theory, and what did we do? We did an example on how to use Kennedy's theory. And what is the other theory that we were going to discuss today? Lacey's. And tomorrow's class we are going to see longitudinal sections. So what sections have we been looking so far? So far. So what section did we design yesterday? Trapezoidal. So is it longitudinal or cross section? So we have designed a cross section. So tomorrow we're going to see longitudinal section and a little bit more about cross sections as well. So in cross sections we are going to see about earth spilling. So when you want to construct a canal, so we are going to excavate or fill earth. So that we are going to see in tomorrow's class. So now we are going to start with Lacey's theory. And let me start with this sketch. What is this? Bed. It's a bed of the channel. And what are these? Sediments, earth's material, right? So what is this? Uniform flow. So you have uniform velocity distribution. Now what would be the impact of these sediments on this distribution? So it would provide resistance and yes, make the flow non-uniform. So you have heard of turbulence. Turbulence, right? So how does turbulence get generated in this? Because of these particles, you get small rotations or eddies, and that keep growing in the vertical direction. So as the flow is moving on top of the sediments, you will slowly start to see that the uniform velocity has changed, and then ultimately it would reach logarithmic profile. And this layer where the velocity is increasing, so the velocity would be increasing from the bed, and after a certain height it becomes constant or uniform. So this you might have heard of boundary layer. Now what did Kennedy give? What is Kennedy's equation for velocity? So what Kennedy considered was the velocity is changing along the depth because of the eddies generated from the bed. But what Lacey says, so when you have a trapezoidal section, you would have eddies coming in from the sides as well. So not only from the bed, but from the side slopes as well. So that's why in Lacey's theory, he modified the empirical equation. So instead of considering the depth y, now the velocity is a function of hydraulic radius. So hydraulic radius, you would consider the wetted perimeter instead of just the flow depth, right? So based on this, he gave the empirical equation as so 2 by 5 F multiplied by R. So F is a silt factor. Silt factor, and it depends on the sediment size. So it depends on the diameter of the sediment. So 1.76 times square root of mr, or you could say square root of d, which is the mean diameter of the sediments. Because so far we have been using d for sediment size, so we will continue with that. So this is one relation for velocity, and then the other relation he gave is for the area and velocity as a function of F. So this is another empirical equation that Lacey gave for designing the canals. And considering the hydraulic radius and the bed slope, you can also calculate velocity based on this empirical equation. So now we have two relations for velocity and one relation for area. So these are the three equations that we are going to use today. So these are the three fundamental equations that Lacey gave us to design the channels, right? So now based on these three fundamental equations, we are going to derive some more relations that are going to be helpful in designing the channel. We are going to derive is, let's say I know a discharge Q, so I want to draw some discharge Q into the canal. Now I want to derive what is the perimeter as a function of Q. So we have these three fundamental empirical equations. So we have to use these three to derive an expression for perimeter T as a function of Q. So Q is AV. So if you use Q equals to AV, and P we have to get as a function of Q. So who wants to do it? So use these three equations to rearrange the terms and then arrive at P and Q. What did we get? So you just need to simplify these two equations, AF square, and then you have B. So R is A by P. So if anybody got the answer, you can enter there. So let's try this. So either you can scan this QR code or go to slido.com and enter this code. Then you would have access to this. You can enter an answer. So V power 4 is this, and replace that here. So replace this V with this. Or you have F squared here and you have F square. So bring F square here and F square, and then equate these two. You need to type the answer. Somebody put in the same code, but you need to type the answer. What you should get. So just rearranging the terms. So you have two equations and then R equals to AP. So if you rearrange, you would arrive at this expression. Somebody got it? Now what about QF relation. So what would be the relationship between V, QF? So if I want to get V as a function of Q and F. So let us say I want to design a channel, and I know what is the discharge, and I know what is the sediment size. So then I can calculate F. Then I have two known parameters, and based on these two, we should calculate what is the velocity V. So what relation would you get? So now let's try VQ here. So what would this relationship be? So what if I multiply this with velocity? We have AF square equals to 140 V power 5. So I'm going to multiply this with velocity V. Then I'm bringing in QF square. So AF square V equals to 140 V power 6. And AV would be our discharge Q. So QF square equals to 140 V power 6. And if I want to calculate V, there are 2 active participants, 4 participants are typing, that's good. And then we have 3 other relationships that we need to derive. So one is slope, S is the slope of the channel, and F is the silt factor, and Q is the discharge. And again, SFR is the hydraulic radius, SFQ, this is the discharge per meter width. Slope, how can we bring in slope? So we have to use the third equation, which is V equals to 10.8 times R power 2/3 and S power 1/3. And how do we bring in F into this? first is also a velocity and the third is also a velocity. So you equate both the velocities. But the only thing missing here is the discharge Q. So you have to bring in the discharge Q into these two equations. Can you see these equations? How do we bring in discharge into this? So R is A by P. If you multiply by velocity and divide by velocity, then you would get discharge Q. Right, do you follow? So you have R. So within this R, you multiply with velocity P. So you have A power 2 by 3, right? So you have A power 2 by 3. So multiply with b power 2 by 3 and divide by b power 2 by 3. And this becomes your q power 2 by 3. Yes. You would have now how do we eliminate this p? 4.75. We have a relationship between p and q. Have you got it? SFQ. So we got one response for S. Yeah. So that is the relation you would get for S. So it's just simplifying the equations that we have. So we have three fundamental equations and we are just trying to play with the parameters that we have. Now what about SFR? So this is simpler. So there is S, F and R here. Yeah, so if you equate these two and simply you would get SFRH. So SFR. So you can type in the same page for SFR if somebody has got the answer. Power 3 by 2 or power 1 by 6. We got one more SFQ. What about SFR? So any other answers for SFR? So we got one answer so far. So do all of you agree with that, or somebody else got any other? So you got a different answer? What is it? Minus 1 upon 2. So now we have two answers. So r power 1 by 6 or r power minus 1 by 2? Minus 1 by 2? Yes. So that's 0.0002 f power 3 by 2 and r power minus 1 by 2. Did anyone catch up so far until SFR? Or anyone still working on this? So we got the last relation now, SFQ. So Q is the discharge per unit width. Now we got a new parameter, W, which we have not seen so far. So we need to kick this guy out. So he does not belong here. How do we do that? So where do we use the width in calculating which parameters? Perimeter. So if we are taking a wide channel, then what would that be? For a wide channel, what is the perimeter? B, width. Or instead of width B, you can use P. So now you get Q upon P, which you have a relationship. Or, so Q upon P is actually, in this case we are taking this as Q, small q. So what would this become? SFQ now. So if anybody got any answers, you can type in here. Which equation do we start with out of these three? So we want a relationship for SFQ. Where do we start? So the third one. So where we have R, S, and B. So our discharge requires area times velocity, and we have done it. got one answer, 0.0002 f power 5 by 6. Then there is a factor here. So maybe you can simplify that. So it is 1.35 power 1 by 3. And also check this power for Q. The power for Q doesn't seem right. So the first part is true, 0.0002 f power 5 by 6. And any other answers for the remaining part? We got it until this 0.0002 f power 5 by 6. Now the question is, where does Q belong? So what is the power for Q, small q? 1 by 3? Who's saying it? 1 by 3? So this is 0.0002 f power 5 by 6 divided by q power 1 by 3. Zero 0.45. No, maybe you can simplify this. So it should be 0.000178. So you can round it off to 0002 or so we have derived these relations, and in tomorrow's class we are going to see how we design a channel based on these relations. So we are going to apply Lacey's theory and design a channel, right? So before we conclude the class, now let's say the question is, what did you learn in today's lecture? Sorry, not that. Alright, so what did we learn in today's lecture? So I want you all to type in. some keywords that you are taking away from today's class. Three responses. Have you seen this? This is called a word cloud. So if there are more number of repeating words, that would appear bigger. So many of you have used the term cherry, so it is bigger in size. Who's their money? This is somebody is sleeping.